Yeah.
That's great.
I was just looking at this log function that we graphed in the last lesson. Y equals log base 2 of x plus b. I started to think that maybe I could just distribute the log so that I get y equals log base 2 of x plus log base 2 of b. I guess I'm saying that I think these are equivalent expressions, so I could write it this way. Log base 2 of x plus b is equal to log base 2 of x plus log base 2 of b.
I don't know about that. Logs are tricky. I don't think that you're doing the same thing as when you distribute a number.
I just know that there's something going on with these logs. I just graphed f of x equals log base 2 of 4x. Here it is. It's weird because I think that this graph is just a translation of y equals log base 2 of x. Is it possible that the equation of this graph can be written more than one way?
When you say a translation of y equals log base 2 of x, you mean a vertical or horizontal translation? What could that equation be? I wonder why the vertical shift turned out to be up 2 when the x was multiplied by a 4. I wonder if it has something to do with the power that the base is raised to, since this is a log function. Let's try to see what happens with y equals log base 2 of 8x and y equals log base 2 of 16x. Oh my gosh, I think I know what's happening here. Here's what we see from the graph. Log base 2 of 4x is equal to 2 plus log base 2 of x. And log base 2 of 8x was equal to 3 plus log base 2 of x. And log base 2 of 16x was equal to 4 plus log base 2 of x. Here's the brilliant part. We know that 2 is equal to log base 2 of 4, and 3 is equal to log base 2 of 8, and 4 is equal to log base 2 of 16. So log base 2 of 4x equals log base 2 of 4 plus log base 2 of x. Log base 2 of 8x equals log base 2 of 8 plus log base 2 of x. And log base 2 of 16x equals log base 2 of 16 plus log base 2 of x. I think it looks like the distributive thing that you were trying to do, but since you can't really distribute a function, it's really just a log multiplication rule. I guess my rule would be log base 2 of a times b is equal to log base 2 of a plus log base 2 of b. So I wonder if a similar thing happens if you have division inside the argument of the log. I'm going to try some examples. If my theory works, then all these graphs will be just vertical shifts of y equals log base 2 of x.
You're definitely brilliant for thinking of that multiplication rule, but I'm a genius because I've used your multiplication rule to come up with a power rule. Let's say that you start with log base 2 of x cubed. Really, that's the same as having log base 2 of x times x times x. So I can use your multiplying rule and write log base 2 of x plus log base 2 of x plus log base 2 of x. I notice that there are three terms that are all the same, so that makes it 3 times log base 2 of x. So my rule is log base 2 of x cubed equals 3 times log base 2 of x. If your rule is true, then I've proven my power rule.
I don't really think it's a power rule unless you can prove that it works for any power. You only showed how it might work for 3.
Oh, all right. Okay, I'm going to say that it can be any number x raised to any power k. My power rule is log base 2 of x to the k equals k times log base 2 of x. Are you satisfied? Before we win the Nobel Prize for mathematics, I suppose we need to think about whether or not these rules work for any base.